There's many, many things that need to be done. So I'm not trying to publish, so you can download the software, you can play with it, it's free for research. But just to give you a sense, what are we talking about? What kind of machines are these that we're building? Basically, it's a bunch of software. At the core of it, there's a runtime engine that runs these hierarchies. There's lots of nodes. They can be very big or small. And you might want to run on anything from a single core CPU on a laptop, which it'll run fine. You can run on a multi-core CPU. We can use all those cores because it's all parallel processing. And you can run on a big cluster computer, which is what we do most of our development on. This system takes care of all the details. You don't have to worry about it. It just sort of takes care of it. There's a second component to it, which is a bunch of tools that let you create these environments, create these hierarchies, test them, and train them. We created a bunch of tools. There's a third-party company that's already created some other new tools, and some other people working on it. So the tool sets are getting better. And then there's a third component here, is the learning algorithms themselves. I said it's pretty simple. You're learning sequences. It sounds really easy. It's actually not so easy. And there's several ways of doing it, and some work much better than others, and we're figuring that out as we go. So you can plug in new learning algorithms as you do this. Now, just so you get a sense of what can you do with this stuff and what's been happening. We think we have about 100 to 200 active developers today. These are people, we have thousands of people who've downloaded it, but we think there's about somewhere between 100 and 200 who use it daily. This tool set. And this is a very difficult tool set to use. This is last year's tool set. We have 8 corporate customers who pay us money to have a very close relationship with us. The applications are all over the map, what people want to do with this and what they're having success or and difficulty with. I'm just going to give you some flavor from. We've been surprised at a number of people in the gaming industry who want to use it. For one, people doing this motion capture inference, figuring out what people are doing as they play with a game. Other people doing for visual editors and so on. We're working with a major car company who's trying to use it to basically understand traffic around a car as you're driving along. Is a car likely to change lanes and so on? Can you predict what's going to happen in traffic? We're doing a bunch of things with voice. A lot of government contractors are using it for voice speaker ID and so on. A bunch of people doing vision-type applications of various types. Process control. It turns out you can take manufacturing data and you can feed it into the stuff, and it kind of discovers what the cause is, and you can do inference and figure out what's going on in there. People are trying to use it in financial markets and so on. At Numenta, we have decided to do a very high-end, a real good vision system as our test case. This is to test out the tools, to test out the algorithms. So we've gone from those little line drawings. We're now doing sort of high-resolution black and white images. Color is actually pretty easy, but we don't want to we want to do the harder problem, which is black and white. So these are the kind of objects we're training on now: cars, real-world objects, cars and boats and binoculars and sneakers and so on. And we have a fairly sophisticated system for getting training data and so on, making movies out of it. And then you can, after the system's been trained, you can give it novel patterns. You clip them off the web. And this is like, these are patterns it wasn't trained on. We say, here, what's this? And these are showing examples of images that got correct. These, I know those are boats. I know those are cars. I know those are binoculars. Totally novel patterns. We're getting close to the cat and dog problem. And I think we'll solve that fairly shortly within the next year or so. So this is our test case, what we're doing with this stuff. Now, I want you can say, what does this stuff do again, right? Let me remind you what it does. You build these hierarchies. You train them on data through some sort of sensory organ. It could be like vision, or it could be just financial data. And the system trains. And what it does is it discovers the causes underlying the patterns. What are the underlying causes from these sensory data coming in? It'd be like discovering, if you were studying weather, it'd be discovering like, oh, there's storm fronts, or there's El Nino. You're trying to figure out what are the underlying causes of manufacturing problems, or the underlying causes of visual input. Once you've trained the system and it's discovered those causes, which is valuable in its own right, you can do inference. Inference is just pattern recognition. You can do spatial and temporal pattern inference, or pattern recognition. The system can do predictions, and prediction, believe it or not, is just the flip side of behavior. The way you generate behavior is exactly the way the brain does it is exactly the way it does predictions. It's essentially that pattern flowing down the hierarchy. We haven't built that, we haven't tested it yet, but we think we know how to do that. And then it's also, you can use a hierarchy for attentional systems, which I didn't talk about, but when you want to do real inference on real world stuff, you have to be able to attend to different parts of the scene or different parts of the input, and it's very good at that. And of course, it can work on any kind of input. You can do like vision, auditory, tactile, human type of stuff, but it works on many non-biological problems as well. This is the basic of it. It's a very fundamental computing paradigm. The question that we could ask here, does it solve the issues that AI has dealt with? And I believe it does. The first issue was one of efficiency. Remember, we had to store lots of knowledge of the world. It didn't seem possible. Well, HTMs, hierarchical temporal memories, are very efficient. And the reason is because of the hierarchy. Things lower down in the hierarchy are reused at the next level up, and those are reused at the next level up. So if I've spent a lot of time learning what certain animals look like, and then I'm exposed to a new animal, it's likely going to have fur or skin or scales or feet or eyes and so on. I don't have to learn all that stuff again. The low-level structure of the world is consistent across these things. It's not like some completely new patterns. And so we basically reuses that, and it makes the storage very efficient, and it makes the time to train very efficient. What you discover when you start working with HTMs is that when you first start training them, it takes a long time to get the first few layers trained, but then it gets much, much faster. It's just like a human. You spend many years basically look like you're not learning anything. As a little baby, but you're actually forming the foundation of this hierarchy, and then the learning gets very rapid after that, and that's the way these systems work. The second problem of AI knowledge representation was one of knowing what to store. And these systems are self-learning. You don't get to choose. You don't get to pick, this is the knowledge I'm going to extract from the world. It extracts it on its own, and that's a good thing, because we know how to do that. And the third thing is, how do you get the information in a way that's useful? You know, what's the structure of it? And HTMs generalize. They generalize in many different ways. And the way they do that is the way the data is stored is not ad hoc. You don't get a choice where it goes. Remember on the paper tape, you know, you can stick the information anywhere you want. Here you don't get that choice. And the way it's structured is a way that it gets to reuse elements in the hierarchy, and it solves those problems. The last point on this slide is just, some of the math people in the room might appreciate this. There's a thing called the no free lunch theorem, which says that no learning algorithm can be better than all other learning algorithms for all problems.